All right, hello everyone. Welcome back. Now, in this lesson, we're going to explore one of the most fundamental topics in biostatistics, that is probability. Now, probability is the foundation of statistical inference. The reason being is that it helps us to measure uncertainty, make predictions, and determine the likelihood of events happening in real-world scenarios that we live in. So in this lesson, we'll cover three main topics: the probability rules and theorems, where we understand how probability works and when events are independent or dependent, meaning independent events do not affect each other, while dependent events do. Then we will cover common probability distributions, exploring the normal, binomial, Poisson, which is a French word, we'll get to that, and exponential distributions. Now don't worry if this doesn't make sense right now. I will go through this. And also we will cover the central limit theorem, which is one of the most powerful ideas in statistics, essential for making accurate predictions. Now, by the end of this lesson, you will be able to apply probability concepts to biostatistics and understand why they're crucial. Okay, let's get started. Okay, so first, let's start with the basics. What is probability? Probability is the measure of how likely an event is to occur. It is expressed as a number between 0 and 1. The probability of 0 means an event will never happen, while the probability of 1 means it is certain to happen. For example, the probability of flipping a fair coin, which means heads on one side, tails on the other, and getting heads is 0.5 or 50%. That is because there are two equally likely outcomes, heads or tails. Now, the probability of rolling a 6 on a fair die is 1/6, because there's only 1/6 and 6 possible outcomes. However, there are a few important rules that probability follows. The probability of any event, which is P, must be between 0 and 1, as I mentioned. As an example, again, the probability of rolling a 6 on a fair die is 1/6, because there's only 1/6 and 6 possible outcomes. The sum of all possible outcomes must equal 0. So the probability of rolling a 1, 2, 3, 4, 5, or 6 on a die must add up to 1. So the probability of rolling a 1 through 6 on a die must add up to 1. And the addition rule for mutually exclusive events, which means two events cannot happen at the same time. So the probability of either occurring is the sum of their probabilities. As an example, the probability of rolling a 1 or 2 on a die is 1/6 plus 1/6 equals 2/6, or 0.23 chance. And then the multiplication rule for independent events is if two events are independent, their joint probability is the product of their individual probabilities. Okay, let me give you an example for this. So if you flip a fair coin twice, the probability of getting two heads is 0.5 times 0.5, which equals 0.25 or 25%. So we want to learn about conditional probability and independence. So conditional probability is the likelihood that an event occurs given that another event has already occurred. In a real-world setting like healthcare, we often use conditional probability to make prediction or assess risks based on known conditions. As an example, what is the probability that a patient tests positive for a disease given that they already have symptoms? We're narrowing our focus only to patients who have symptoms and asking how many of those test positive. What's the probability of heart disease, as an example, given that a patient is overweight? Again, we're not looking at the entire population, just the overweight individuals, and asking how many of them have heart disease. Okay, so the formula for conditional probability is the probability of A given B equals the probability of A and B divided by the probability of B. Now, what these symbols mean is that the probability of A given B is what we want to find. So that's this part here, the probability of A given B. Then the probability of both A and B happen here, and the probability that B has occurred are down here. So let's give an interpretation in a hospital context. Let's say that A is testing positive for a disease. Let's say that B is showing symptoms of the disease. Then we calculate the chance of a positive test among patients who already have symptoms. So again, it is the probability of A given B up here divided by the probability that both A and B happen down here. Makes sense, right? Okay. Now let's move on to probability distributions, which describe how probabilities are spread out across different values. Now, in biostatistics, we use different distributions to model real-world situations. There's the normal distribution, which is one of the most important probability distributions, and it's shaped like a bell curve, meaning that most values cluster around the average or mean with fewer extreme values on either side. Many things in nature follow a normal distribution. As an example, human weight, or blood pressure, or IQ scores. All of these typically follow a normal distribution, where the properties of a normal distribution might include symmetry, meaning that it's perfectly balanced around the mean, the 68, 95, and 99.7 rule, which is meaning that 68% of values fall within one standard deviation, 95% within two standard deviations, and 99.7 within three standard deviations. Now, there's other important distributions, like binomial distribution. This is when an event has only two possible outcomes, such as success or failure. An example might be probability of a vaccine working or not working in a clinical trial. Then we have the Poisson distribution, which models the probability of rare events happening in a fixed interval. An example might be the number of patients arriving in an ER per hour. Then we have the exponential distribution, which is used to model time between events in a process. As an example, the time between heartbeats in a medical study could follow this exponential distribution because there's time between events within the process. Now, finally, we get to talk about the central limit theorem, or the CLT, which is one of the most important ideas in statistics. The CLT states that if we take many random samples from a distribution and calculate their means, those means will form a normal distribution regardless of the original population's shape. So this matters because it allows us to make accurate predictions even when data isn't normally distributed. And it really helps us to estimate population parameters using sample data. This is why larger sample sizes lead to better estimates. They follow a normal distribution even if the data itself doesn't. Now that's important. Okay, today we covered probability rules and theorems, conditional probability and independence, common probability distributions, as well as the central limit theorem. So thank you for watching. I'm glad you were able to learn with me, and we'll see you in the next lesson.